Hey everyone, we're going to be looking at a quick little practice problem right here. Let me see if I can lay out the problem and you tell me, you go ahead and try to solve it yourself and then we'll walk through it together. It's a little bit more complicated than normal, so you can break it down into some simpler problems. So let's do kind of a simpler problem first. We have person A. Person A is going to throw a water balloon. This water balloon they're going to throw off the side of this building at 10 meters per second, just straight horizontally. All right, so person A throws their water balloon 10 meters per second, perfectly horizontally, 50 meters above the ground. And we're going to be asking you about where it lands, when it lands, stuff like that. Person B does the same thing, but they don't throw it straight horizontally. They throw theirs down at a 35-degree angle. So you see right here, person B, theirs is going downwards. It's still 10 meters per second. One more little wrinkle here. Person B throws their balloon a half a second past behind person A. So person A throws it, then person B throws it. Ultimately, we have two questions. Which water balloon lands first? And how far apart are they from where they land? Like if we're looking at where they land, how far apart is it? Um, so I'm going to give you a second to try this out. I'll lay this out again so you can see all of it. Which water balloon lands first? How apart do they land? Now, I'll go ahead, if you want to try this problem out, pause it for a second, and then I'll give you maybe some hints on how to go about it. All right? Pause. Okay, so I'm assuming that you've looked at the problem, maybe tried to lay things out. Heck, maybe even solved it. That'd be great. If you haven't, let me give you some tips. This problem is kind of two problems. So let me recommend something. Why don't you try solving the problem all for person A? Let's see, my goodness, if I can draw a line here. Try solving the problem for person A first. Just when and where does it hit the ground? And then do the same problem for person B. So you're literally going to do one of our normal problems for person A, and then you're going to do the same sort of thing for person B. And then you're going to use your answers to those two problems to answer our two questions. So go ahead, try to figure out when and where person A's balloon and person B's balloon lands. I'll give you a second, pause it, and then we'll go through it together. All right, you ready to go? So we're going to go ahead, like I said, we're going to split this into two separate problems. Person A, we don't know what time the balloon lands. We do want to know that. We know that the person A, their balloon starts off at, well, we're just going to call this spot 0 right here. So person A, their balloon starts off at 0 meters. Their final position is actually what we're looking, one of the things we're looking for. Their initial velocity is 10 meters per second, straight to the right. There is no acceleration horizontally. Now, vertically, we know that they start off at 50 meters, so they're 50 meters above the ground. Where are they going to end up? Well, they're going to end up on the ground. That's position 0. So they're starting off at 50 and dropping down to 0. Here, for person A, there is no V naught. The water balloon is not moving up or down at all. And that finally, there is an acceleration of negative 10 meters per second squared. So I'm going to run through this to find the time. Change the color here real fast. I'm going to run through all this to find the time, and then once we have the time, I'll use that to find the position. So let's go ahead and work through the algebra. I'm going to do this all algebraically just because it takes the least amount of space. All right, so Okay, so I end up getting the time it's going to take for this balloon to land is root 10. So I don't have a calculator right now that's set up for you to see it, but you'll have to just trust me. I get that root 10 is 3.16 seconds. So up here, 3.16 seconds seems to be our answer. Now horizontally, position is equal to the velocity times the time plus the initial position. We're going to then get the position is equal to 10 meters per second times our time plus 0. So I'm going to end up getting a final position of 31.6 meters. So for person A, who was yellow, right? Their balloon ends up landing here at 31.6 meters, and it lands after a total of 3.16 seconds. All right, now we're going to do the same exact work for person B. Now, you could, if you wanted to, incorporate the half-second delay. I'm not going to do that. I just want to see how much time it takes for person B's to land, ignoring person A. I'm just going to ignore person A entirely when I'm working on person B. And then afterwards, we'll deal with the fact that it took longer. Now, or that they started later. Now, you could, if you wanted to, include it in your actual math, but I don't think it's worth it. All right, so the initial position horizontally is still 0, and the initial position vertically, are you gonna work today? Sorry. The initial position vertically is still 50. So those are all the same. The final position is still what we're looking for, and the final position here is still 0 meters. Now, the initial velocity is where things change, because here the initial velocity will be 10 meters meters per second times the cosine of, what did I say, 36? Yeah, 35 degrees. Whereas here, it will be, the velocity will be 10 meters per second times the sine of 35. And a quick note, this is downwards. Do you see how we're throwing it down? So this will have to be a negative, whatever that is. There is still no acceleration here, but there is still an acceleration here of negative 10 meters per second squared. So same game plan. We're going to use our y values to find the time. We're going to use the y values to find the time, and then we'll use the time to find the x values. So let's go through it the same way. First, I'm going to go ahead and recalculate our velocities. So again, sorry, I don't have a calculator set up for you. I end up getting the sine, so this is negative 5.7. So that's 5.7 meters per second downwards. And then 8.2 meters per second to the right. So we'll need those two values to throw into our equations. All right, so first one, y is equal to 1/2 at squared plus v naught times t plus y naught. Okay, so how are you going to solve this? Now, we could use the quadratic. I've had a few students want to go through using the quadratic. Tell you what, we'll use the quadratic real fast, and then I'll check it with Desmos, just so you're fine either way, just so you can even see how to do it in Desmos. All right, so if we're going to do the quadratic, we know that it's negative b plus or minus the square root of b squared minus 4ac all over 2a. So that is 5.7 meters per second plus or minus the square root of, sorry, I'll slow it down. That's negative 5.7 meters per second squared minus 4 times 1/2 times negative 10 meters per second squared times 50 meters all over 2 times 1/2 times negative 10. Okay. So give me a second, just go ahead and calculate through this. I end up getting, when it's all said and done, 2.6 seconds. All right there. Oh, yeah, 2.64 seconds. I did it kind of quickly because we're on video, so I would not be horribly surprised to hear if I messed that up. That said, compared to what we got for this other problem, it seems like it could be right? Doesn't it? It goes a little bit faster than the other person's. It hits the ground faster than the other person's because they throw it downwards. So let me show you how to throw that into Desmos real fast. So the way we would throw this into Desmos is first I have to show you my Desmos. There you go. The way you throw this into Desmos is you just type in the equation, the whole thing, except for the landing spot. I'll just go ahead and do that. So it's our y value is 1/2 times negative 10. You can keep it as t, and then we've subtracted from that. Let me go back and check. What was it? 5.7. 5.7 times t plus 50. We go ahead and look right here, and sure enough, 2.643. See, I'm just mousing over it right here. It shows me where the 0 is. So it's at 2.643. So that is the time at which this thing is going to hit the ground. And look, we did it just right. Good. My quadratic formula is not horrible. All right, so let's go ahead and figure out where this hits. So if our time is now 2.64 seconds, so our time is now 2.64 seconds. Let's turn off the Desmos. We know that our position will end up being the velocity, which we figured out was here the 8.2, our horizontal velocity, times that time, 2.64 seconds. I end up getting 20. Oops. I end up getting 21.6 meters. So this balloon does not travel nearly as far, which makes sense because then the other person threw it 10 meters per second straight to the right. This one actually threw it down, so it'll hit a little bit sooner. So it makes sense that it hit a little bit sooner. Now, when does it hit? Now, I'm tempted to say this 2.64, but that is from when they threw it. And remember, the problem is this person threw it a half second later. So it's actually 3.14 seconds. So it barely hits sooner than the other one does. They hit almost exactly the same time. In fact, within a sig fig. In fact, it wouldn't be surprising if their measurements, they hit at about the same time. So, long story short, it looks like person B's balloon will end up hitting the ground. Oops, that's a horrible shape. Will end up hitting the ground about the same time as person A, but person A's will have gone a lot further. All right, really complicated problem, probably more complicated than one I'll give you on the E, but that said, this would be something I expect you to be able to do. Notice it's just two of the normal problems. There's nothing too difficult, there's nothing too tricky or crazy about it. You just have to consider two different moving objects. And because we have two different moving objects, we need two different sets of equations. If you have any other questions about this, if you have any thing you want me to walk you through, if you want for me to check your work, maybe you want to do it graphically or something, let me know. I'd love to look at it. Yeah, so go ahead, take a moment, try this out today, and let me know what you guys think. See you around.